Hey, I'm Philip. I'm going to be answering this question about A being some set that contains the integers from -4 to 4, R being a relationship on A as follows: for all ordered pairs in A cross A, M R N is a way to write M comma N is in R, if and only if 5 divides M squared minus N squared. So pretty much what we're actually doing is we're saying we've got A cross A, right? A set of ordered pairs on A, like 1, 1, or 1, 2, or -1, 1, or -1, -4, just all stuff from A. And we're wondering which of those things are in the relation R. And so R is based on that rule that if you take the difference of squares, like 1 squared minus 1 squared, that equals 0. If that's divisible by 5, then the pair 1, 1 would be an R. On the other hand, we've got the pair 1, 2, right? 1 is an A, 2 is an A, right? But if we take 1 squared minus 2 squared, that would be 1 minus 4, that's -3. That is not evenly divisible by 5. So the pair 1, 2 is not in R. So now we've answered the question, what is R? And I've got some Python code to actually write down what is A and what is R. R is kind of big, but that's okay. And it's okay if you don't understand the code. If you're not CS or DS or whatever, you're like taking just discrete math, that's fine. It's more important that we understand, is R an equivalence relation and why? That's probably what this question was asking. And so, well, how do we know if it's an equivalence relation? And the answer is it has to satisfy the 3 axioms of an equivalence relation. That's symmetric, reflexive, and transitive. So what do each of these mean? Symmetric means if x, y is an R, then y, x must be an R, and vice versa. So really what that means, we've got R here, there's a set. We see the pair 3, -2, right? If R is an equivalence relation, then we must be able to find the pair -2, 3. And we actually do see it here near the end, right? Same goes, I could just pick another random one, is -1, 4. That's in R. Well, we better be able to find 4, -1 somewhere. Look for it. Yes, here it is. And so we pretty much do that for every single point in R to check that one. Well, that's a lot. We don't want to just be looking all day, every pair of pairs, right? If you're CS, you know that's O(n) squared operation, whatever. We do that mathematically to save some time. So it's symmetric, x, y in R, if and only if y, x in R. What does that actually mean? Well, these all come back to this relationship. 5 divides m squared minus n squared, right? So 5 divides -1 squared, okay? 1 minus 4 squared, 1 minus 16 equals 0. 0 is divisible by 5. Just kidding. 1 minus 16 is -15. -15 is divisible by 5. So yeah, that's what I meant to say. And so, how does that help us show that this is symmetric? Well, what if we did 4 squared minus -1 squared? That'd be positive 15, which is also divisible by 5. So this divisibility symbol, we put like a negative sign here, it would still be the same thing, right? it doesn't matter if you're taking the positive or negative. It's either divisible or not, right? So 5 is divisible by 0, positive 5, negative 5, so on. I mean, 5 divides these things. And so, based off of that, knowing that this symmetry relationship, flipping x and y, is really just making positive or negative, and then checking divisibility, we know that R must be symmetric. Okay? The next thing is reflexive. AA has to be in R, and that's for all elements in A. Okay? And so actually, I've got code to show that. We have to check each of these 0, 1, 2, 3, 4, negative 1, negative 4, negative 3, negative 2, that 0, 0 is in R, 1, 1 is in R, 2, 2 is in R, all of them. We check all of them to see, otherwise it won't be reflexive. We do check all of them here, but we could also just think 1 squared minus 1 squared, that's 0. 2 squared minus 2 squared, that's 0. X squared minus x squared, that's 0. 0 is divisible by 5, right? That's what it takes to be an R, so it's got to be true. Last thing is transitive. If AB is an R and BC is an R, AC must be an R. So this is usually the trickiest one. It says if I see 3, negative 2, then I have negative 3, 3. So I could say negative 3 is my A, 3 is my B, and negative 2 is my C. That means I have these two, I have these two. I mean, I should be able to take this one, this first one here, and this second one here. I should be able to find a negative 3 with a negative 2 somewhere here. And I'm sure we will be able to find it. Maybe negative 3 and a negative 2. Yeah, right here. And so why can I do that? Instead of checking, let's do that mathematically. So do a squared minus b squared is divisible by 5. And sorry, my arm is broken, so it's so hard to write. A squared minus b squared is divisible by 5. So we know what that is. Let's try typing it. 5 divides b squared minus c squared. Okay. So now does 5 also divide a squared minus c squared? That is the question that we're actually answering. Yes or no? 5 divides a squared minus c squared. Well, we have to either check all of R or do some math. So, what do we think? Maybe there is some rules we know about divisibility. If 5 divides x and 5 divides y, then 5 divides x plus y, right? Something like this, right? 5 divides x, 5 divides y, then 5 divides x plus y. How does that help? Well, we have these two right here, right? So say this is x, this is y. a squared minus b squared plus b squared minus c squared. Adding these two, we actually get this here. This is our relation. And so we find that it is transitive. And so that concludes what is R an equivalence relation.